In the previous class, we finished analyzing all properties of eigenvalues and eigenvectors, actually mainly eigenvectors, right? We were worried about them being orthogonal to each other, so in case of a degeneracy, we applied Gram-Schmidt procedure in order to develop the way of making them orthogonal to each other, right? And then after that, we could use all those eigenvectors as a basically basis for our solution. So we wrote down general solution for the whole system, right? And we also wrote down a general solution for particular particle, right? So we wrote down something like this, right? Which subscript I use? Eta I, right? So eta I equals to summation over k, then complex form, right? Ck, a I k, and e to the power of minus I omega k t. So that is a general solution describing motion of particle I out of n particles, right? Then the logic for the next step, right? We showed, right, when we looked at the properties of eigenvectors, we saw that potential energy matrix and kinetic energy matrix can be diagonalized, right? And the matrix can be diagonalized. What does it mean? It means that there is some set of coordinates, and if you go there, kinetic energy and potential energy matrix will have a diagonal form, right? And so now, of course, the logical question: how can we find those coordinates? Where should we go in order to have kinetic energy being diagonalized and potential energy the same, right? And of course, as a result, kinetic energy will have only quadratic terms, and potential energy will have only quadratic terms in those coordinates, right? So that was, after raising that question, we started searching for that new set of coordinates, right? And we started with this. So I told you, what if we take this part, right, and call it psi k. That's how basically we started introducing our normal coordinates, right? Right, and also our goal was also sort of locally. Can we write, for example, a coordinate psi1 in such a way, introduce new coordinates in such a way so that, for example, psi1 would oscillate only with the frequency omega 1, psi2 with the frequency omega 2, and so on, right? But that's sort of kind of local goal. The global goal is to find that new set of coordinates where both matrices, kinetic and potential energy, will be diagonal, right? So that's how we introduce it, and then as a result, we can write in a component form this way. So aik psi k, and of course in a matrix form we wrote it like this: a eta equals model matrix A and our column of new coordinates psi. So that's how we could move and can move still, right, from the new coordinates psi, which we call normal coordinates, to the old one. And I told you again in the previous class, so etas define positions of particle. Particle is here, so eta define position of that particle. Psi doesn't have to define position of this particles. They can define positions of some points in the system, right? Okay, and then, so that's how we can move from psi to etas, and then we showed that we can also find and move from etas to psi in this way. So psi equals to what? A transposed T eta. So that's how we can move back again. Column, and these are matrices, right? Okay, so now we can frame this as well, right? So that's what we shown. And so that's how we introduce these new coordinates. Xi, probably I should write xi, normal coordinates. Normal coordinates. So right now it's still the review of previous class. And so, okay, that's how we introduce these normal coordinates. But of course, we need to convince ourselves and everyone else that if we go into these coordinates, that our kinetic energy is going to have only quadratic terms, potential energy also have quadratic terms. Because in that case, potential energy matrix diagonal and kinetic energy matrix will be diagonal. So we need to show it explicitly. So that's what we started doing. And first we looked, of course, at the kinetic energy. So now we're basically moving from etas to xis, right? And kinetic energy we showed it was 1/2 summation over ik t ik and eta I dot eta k dot, and we showed that it is equal to 1/2 summation over alpha from 1 to n, and we ended up with xi alpha dot squared. So that's what we ended up. So great, only quadratic terms. So in these coordinates, xi kinetic energy looks as it should look, right? Based on our goal, right? Based on our goal. So only quadratic terms. Only quadratic terms. And of course, as a result, if you write potential kinetic energy matrix, it will have a diagonal form, a unit matrix with ones along the diagonal line. Okay, so now pretty much that's where we finished in the previous class. And now let's try to do the same with potential energy, right? Again, in attempt to see that we were hoping to get only quadratic terms, but most likely it will be correct. Right. So now potential energy. Again, it's not potential energy matrix, it's potential energy, right? So it is 1/2 summation over ik, then v ik eta I eta k equals. Okay. So now again I will use this basically, right? So eta equals to this stuff, right? So eta I will be equals to that, but instead of k I'm going to use alpha s and then beta. So it will be 1/2 summation. Okay, let me keep it for here for now. V I k, and now instead of eta I, I'm going to have summation over alpha from 1 to n. Alpha instead of this k. Now I'm going to use alpha because k is already used over here. So alpha a instead of I alpha psi alpha, right? And now eta k. So now, of course, since we have a product, we're going to have a product of two sums. Of course, index must be changed. Okay, instead of alpha, let's use beta. Bigger deal, right? So summation over beta from 1 to n. Now it's a k beta and psi beta. Right? Yeah, all parentheses are closed, so it looks good. So now let's arrange it in a better way. Let me take these two sums outside. Okay, 1/2, of course, summation over alpha beta, and then in the parentheses I will keep summation over ik, and now let me arrange this guy. Okay, you see it. It's a I alpha v I k and a k beta. And xi alpha psi beta. What is in this parenthesis? So look, we have inner indices the same. Then this inner index I sort of collaborate with this outer index, right? It means that this matrix must be transposed in order to write this inner matrix form. Otherwise, it looks perfect. Model matrix V and then model matrix transposed, right? So this is equal to not effectively. It's just a component form of this matrix product. A transposed, not T, V. All right, V, A. Congruence transformation of V, we discussed this. This congruence transformation diagonalizes our model matrix. And it is equal, you remember, to lambda. Again, it's a matrix, right? That's why I put a line underneath emphasizing that it's not number, it's a matrix with eigenvalues along a diagonal line, right? But so this is written in a component form. Of course, we can write that it should be equal to what is lambda. It's a component form lambda alpha beta, right? Because summation over I, k, those indices disappears. Only alpha beta will live outside, stay. And we can also write it like this: lambda alpha delta alpha beta symbol Kronecker. We can write it like this also, right? Okay, so now let's use it over here. And this symbol Kronecker is going to kill our sum over one of these sums. It's better to get rid of beta, right? We're alpha. Let's keep alphas. So it will be equal to 1 over 2 summation over alpha from 1 to n, and alpha. Okay, lambda alpha, and again, instead of beta, we're going to have alpha, because this symbol Kronecker is going to helps us to get rid of all betas, right? No betas in our equations, right? Only alphas. All right, so psi alpha squared, right? Okay, great. We're getting quadratic terms only. But now, in order to have the sort of write the final form, of course, we need to recall that lambdas, it's a squares of eigenvalues, squares of our frequencies. So let me write that down finally. Okay, probably I will write it underneath, so it will be where I keep a 1 over 2, probably outside. It's not a big deal. Okay, let's keep it inside. Summation over alpha from 1 to n. Then 1 over 2. Okay, so that will be omega alpha squared and psi alpha squared. Again, only quadratic terms. Okay, let me frame it because, okay, important, right? And this. Only quadratic terms, great. Only quadratic terms. It means what? It means, again, if you write potential energy matrix, of course, it will be diagonal, right? So, yes, it means that in these normal coordinates, which we introduced in this way, xi's, yeah? These are coordinates which we wanted to find. So then, yeah. So no coupling terms, no cross terms, and in this, those cross terms in the potential energy, they're called static coupling terms. Not a big deal if you don't remember that, but no cross terms, static coupling terms, static coupling terms. Right. Okay, so now, since in this coordinates kinetic energy has this quadratic form, potential energy has this quadratic form, so now we can write Lagrangian, and it will be decoupled again because there are no dynamic coupling terms, no static coupling terms, no coupling terms whatsoever. So we can write Lagrangian without coupling terms. But before, let me check if I mention everything about this, and then I think it's time to write Lagrangian. Start writing the Lagrangian. Yeah, yep. Okay. So now I can put a small new bullet. So L, of course, T minus V. Again, it's still Lagrangian expanded using Taylor expansions, because you remember this already after expansions at the very beginning, you remember. And again, this was also after expansions. So Etas were small. Of course, as a result, Xi's are small. So Lagrangian can be written as, of course, okay, I will drop summation, so it will be Xi. Okay, for whatever reasons I use K subscript. Oh, Xi K squared, and minus omega K squared, Xi K squared. So that's the Lagrangian. Okay, maybe I should frame it. So again, no coupling terms. So Lagrangian is decoupled. L is decoupled. That's the goal of any possible simplification of the problem. If you can write the Lagrangian, which is decoupled, what else can you dream of, right? Right, and so now Lagrange equation, right? So we can write Lagrange equation. So for k, for index k, so dl over partial derivative with respect to psi k minus partial derivative of Lagrangian with this dot psi k equals to 0. So all equations, differential equations, second order partial differential, or not second order differential equations, sorry. Second order differential equations are going to be decoupled, of course, right? If Lagrangian is decoupled, equations are going to be decoupled. So we can write it as psi k double dot, minus from here, minus from there, plus. So it will be plus omega k squared and psi k, and equals to 0. Right. Decouple differential equations. Again, it's deserve a big happy face. So basically it means what? In these coordinates, psi, in normal coordinates, basically system represents as a system of n isolated, basically, right? Isolated simple harmonic oscillators, which are oscillating just by themselves, right? Without basically like interacting with each other, right? Completely independent. So these coordinates size declare their independence, basically, right? And it means what? It means that they don't share energy, right? If some amount of energy stays in with this coordinate, okay, it stays there. No energy transferring, and so on, right? So in this, yeah, we have, as a result, we have mathematically we have n equations of simple harmonic oscillators. Right. Okay, solutions, yeah, piece of cake. right? We've done it in undergraduate level course. Psi k equals to constant ck and e to the power of minus I omega k t, right? And basically that's what we were searching for psi k in the very beginning, right? So our normal coordinates, and that's what we got over here. So what else I wanted? Okay. So let me write down a few solutions for a few xi's. All right. So psi 1, of course, it will be c1 e to the power of minus I omega 1 t. You remember our sort of local goal. We wanted to introduce such a coordinates where psi 1 would oscillate only with frequency omega 1 with the frequency of first normal mode. Then if I write psi 2, of course it would oscillate only with the frequency of the second normal mode, c2 e to the power of minus I omega 2t, right? And the last one, of course, it will be for n psi n equals to c sub n e to the power of minus I omega n t. Because initially ADAs oscillated with all possible frequencies of all normal modes. Now psi 1 only with omega 1, psi 2 only with omega 2, and so on. So basically it means what? And again, omega, it's a characteristic feature of a normal mode number 1. This is a second normal mode. Basically, the first normal mode is all here. In the first normal mode, psi 1 oscillates with the frequency of the normal mode. What do the rest of the particles, the rest of the coordinates do? Nothing. In the first normal mode, psi 1 oscillates, but psi 2 will be equal 0, psi 3 equals 0, and so on. All the rest of the coordinates will be at rest. Again, in the first normal mode. Right? Again, you remember the first normal mode, the major feature. All particles oscillate with exactly the same frequency omega 1. In this case, psi 1 oscillates with omega 1, the rest just at rest. Then its second normal mode, psi 2 oscillates with the frequency of the mode, but psi 1 will be at rest, and the rest of the psi's will be also at rest. But in ATAS, you take any normal mode, and all particles in general, of course, all particles oscillates. All right, with that frequency, with the frequency of omega 1. But in this case, only one of the coordinates. Every time, force of habit, I want to say particles oscillates. No, because these psi's, no one can guarantee that they're going to define position of the particle. Right? Most of the time, they just define a point in the system, right? So in this case, every time I'm trying to force myself, coordinate oscillates, right? Coordinate oscillates. Right. Okay, so now, let me write what I just told you about the normal modes. All right. So I can write, so the problem is reduced to a set of n independent simple harmonic oscillators. So the problem is reduced to a set of n independent simple harmonic oscillators. Right. Again, in size, in these normal coordinates. And so now about these normal modes, which I just told you, right? So let me write a few things. So first, normal mode. So what? Only Psi1 oscillates. Of course, with the frequency of the first normal mode, because that's the major feature of normal modes. Normal mode 1, frequency omega 1, normal mode 2, frequency omega 2. Right? And and the rest psi 2 and all the way to psi n are at rest. Okay, the rest are at rest. Sounds funny. Okay, I didn't plan it, right? The rest are at rest. Right, then similar we can say about the second normal mode. Second normal mode, psi 2 oscillates, of course, with omega 2, and then the rest, and then psi 1, psi 3, and all the way to psi n are at rest. They don't oscillate, and so on, right? Okay, I'm not going to rewrite. I don't want to write more. Then this. And maybe I can write, so yeah, all these psi's are independent and no energy is transferred to or from them, as I told you, right? Okay. Okay, so now at this point, it's great, right? So that you can find such a great coordinate psi, right, where Lagrangian is decoupled, system consists of n independent simple harmonic oscillators. Everything is beautiful, everything is great, but the question is, how can you get these psi's? I wish we could knew how to get these psi's from the very beginning when you start looking at the problem. But there is no procedure so that we can get these psi's from the very beginning, so that we can write the Lagrangian in terms of them, and solutions is trivial, right? Look, how can we get those psi's, right, according to our procedure which we've developed? You need to start from the very beginning, right? Find those matrices, right? Find eigenvalues, then eigenvectors, write general. Actually, eigenvectors is at that point is enough. Then you can write down model matrix, and only then, once you know all eigenvectors, so that you can write model matrix. And of course, I assume that you already wrote from the very beginning kinetic energy matrix. So only then you can move from etas to psi's. So pretty much you need to solve the problem in order to introduce psi's. So what a what a big deal, right? Yeah, of course, if you want to dive into the problem, into the system deeper and analyze it later, right? Then probably it makes sense after you found etas, you will move into psi's, and it will help to simplify your life in your deeper analysis of the system. But first, you need to solve the problem in terms of etas, and only then, right? Again, as I said, I wish I wish we could somehow write this psi's from the very beginning, right? Before solving the problem. Okay, most of the time it's impossible unless if the problem is reasonably nice, then you can apply some tricks and you can find psi's from the very beginning, right? Next class we will look at a couple of examples, and of course just naturally, okay, not naturally, just we will look at a couple of examples where we could guess, not guess is the wrong word, we can deduce um, uh, and write down normal coordinates from the very beginning, right? Basically, we will be able to connect ATAs with XIs from the very beginning. But again, it's only possible if the system is reasonably nice, reasonably simple. Not completely trivial, but reasonably simple, right? Okay, but otherwise, it's still um, tedious procedure writing kinetic energy, potential energy, then solving finding eigenvalues, eigenvectors, writing model matrix, and only then you can get only to these normal coordinates. Right. Okay, so now after this, let's start looking at examples. Pretty much now we exhausted everything. Right. So let's start looking at examples. And first example, yeah, more or less classical, linear triatomic molecules. At the center, I will draw the bigger, like my head, particle, and then two particles on the sides, right? It's an oversimplified version of CO2 molecule, right? CO2 molecule, right, with all possible oscillations, right? But of course, in a real CO2 molecule, it's not a linear molecule, right? It's like I used to work at STL, and there's one physicist, right? Since STL uses CO2 lasers a lot, right? So of course you need to know all possible modes of molecule CO2, right? And he likes showing some funky moves with these possible oscillations of molecule CO2. I still remember them. Okay, so anyway, let's look at the molecule. And you know what? I will probably start erasing this because we will need lots of space, and I want to have picture in front of us somewhere at the top all the time, right? Right, we can erase it all. Yeah, probably erase. So, linear triatomic molecule. So, example, I can put a new bullet. Linear triatomic okay, approximately CO2, for example, right? Because again, CO2, of course, is not linear molecule. Okay, so let's start with the picture. Okay, let's say the first one, black one, let it be at the center. And then there are two smaller molecules. Let me draw them here. Right. And of course, the interactions between them can be modeled with springs, right? And of course, spring constants must be the same because here interactions must be the same and they're the same because we have symmetry relative to the center, symmetry of the molecule, right? So it will be K, K. Now masses, mass of this, let's say it's M small, this will have M capital and M small. So that's the system. Again, immediately we're imposing constraints that this particle moves only along this horizontal line, right? So first, since we use Lagrangian formalism, so of course initial coordinate system must be inertial, right? And then we apply Taylor expansions, right? And moved from original coordinates coordinates axis to etas, right? Okay, so original coordinate system is x. Let's say this is origin, right? So of course this is inertial, right? Reference frame. And so let's say this is current position of the particle, this one, x1, current position of this particle, x2, current position is x3. And of course, we need to know the equilibrium points. Let's say the equilibrium point of this, which way I label it? 0, 1, okay? 0, 1, this will be x02, and this is x03. And again, the most convenient, of course, coordinates, etas are displacement. Okay, after normal coordinates, the most convenient. But of course, as I told you from the very beginning, it's next to impossible to get normal coordinates. So we have to go through the procedure which we've developed. Right, so for now, the best is eta 1, eta 2, and eta 3. So these, so far, the best coordinates, right? So we have 3 degrees of freedom system, right? And so we need to introduce 3 coordinates etas. And so, of course, what's the transformation equation? So eta I, probably I will write, let me write eta I equals to xi minus x0i. So that's the transformation equation, time independent, everything is good, like you remember a few classes ago when we started setting up the problem. So transformation equations must be time independent, so it's correct. So we're moving to etas. And so now we need to, and of course they are small, right? Etas are small. And now we just need to write down kinetic energy and potential energy, right? Again, in terms of these etas. And in this case, we can easily write it down. Okay, so let's start with what? Etas. Yeah. With potential energy. Potential energy. So V equals, right? So again, gravitational potential energy is out of the question because it's either 0 or constant. But anyway, we can ignore it, right? Because they're at the same level, right? So only spring potential energy, but we can easily write that down. So it will be k over 2. Basically, we need to write down square of stretching of the first spring. Of course, stretching is determined by the difference between eta 2 and eta 1. Which one is bigger? And so it will be eta 2 minus eta 1 squared. Okay, so that's the first part of the potential energy. And now, similar, we need to write for the second spring. Plus, again, k over 2. And now eta 3 minus eta 2. Eta 3 minus eta 2 squared. You can write eta 2 minus eta 3 squared. It doesn't change the game. Anyway, square. They squared. Okay, so now let's write explicitly. Okay, let's just open brackets. All right, so I'll probably take k over 2 outside. Yeah. So of course it will be eta 1 squared plus eta eta 2 is over here and eta 2 over there. So we'll have 2 eta 2 squares. Eta 2 to the power of 2, right? Here's 1 and there 1. And 1 eta 3 plus eta 3 squared. And then cross terms. So from this minus 2 eta 1 eta 2, and then from there minus 2 eta 2 eta 3. That's it, right? Okay, now we have to be careful. First, one of the most typical mistakes, not many students, but classes are small, right, usually. But a few students made this mistake. 1 over 2 is not part of the potential energy matrix. 1 over 2 we keep outside. we're not introducing it in potential energy matrix. And the same about kinetic energy. So I've seen in the past, every semester, 1 or 2 students made this mistake, so be careful. Then, of course, we need to be careful with these cross terms. All right. So let me, at the very beginning, let me do this. Let me, of course, split this into 2 terms. It will be minus eta 1, eta 2, and minus eta 2, eta 1. And of course, this I can do the same. Eta 2, okay, minus eta 3, and minus eta 3, eta 2. So that we wouldn't lose any terms. And now let me write potential energy according to the expression which we introduced a couple of classes ago. Pretty much, let me write all possible terms, and then by comparing we can construct the matrix just to be safe in this example, in the first example. And then it's up to you how you feel, how confidently you feel, right? Of course, you can skip plenty of steps. You can write potential energy matrix immediately right away, right? But let me do it first this way. So V, of course, we wrote it down is like that. 1 over 2 summation, which okay, I can skip summation, right? V I j eta I eta j, and of course I can write all possible terms. Again, 1 over 2 I will keep outside, and it will be V11 eta 1 squared plus V22 eta 2 squared plus V33 eta 3 squared. I'm just writing all possible terms. Pretty much there will be 9 of them, right? 3 by 3 matrix, 9 terms. Now cross terms, plus. So it will be V12 eta 1 eta 2 plus V21 eta 2 eta 1 plus V, let me keep which 3 1 3 2. Okay, let's use 2 3 eta 2 eta 3 plus V 3 2 eta 3 eta 2, and the last 2 terms, 3 1 3 and 3 1. Okay, I wouldn't be able to fit probably. So plus V1 3 eta 1 eta 3, and plus V3 1 eta 3 eta 1. Okay, so now let's construct the matrix V. Let me write it over here. Right. So yeah, V11, again, 1 over 2 is outside. V11, it's K must be taken, right? So it's K. Then 2 K. Then 3 3, again just K. Right now off diagonal elements, right? So V12 1 2, it's okay, K again, minus K, just 1, not 2. So minus K, so because we split it, so it will be minus K, right? And you remember all these matrices are symmetrical, right? So relative to diagonal. So if here minus K, immediately I can write minus K over here, right? So now which is this term? Now V 2 3, V23, it's at this term, V23, it's at that, again, minus K, and of course, because the matrix is symmetrical, there must be minus K over here, which is this term, right? No, this term. And V13 and V31, it's not in our actual potential energy expression. So it means that these are 0, 0, right? So that's our potential energy matrix. Of course, you can, once you know what you do, of course, you can skip these steps. You can write immediately, basically. But careful, because, you know, we're all human and we can make some silly mistakes, like in the exam too, right? Right. Okay, so that's potential energy, and now kinetic energy matrix. Right, that's simpler. So let me put here the first bullet, now the second bullet. So kinetic energy. matrix. All right, so kinetic energy of the first, second, and third particles, very simple. So it will be m over 2 eta 1 dot squared plus m capital over 2 eta 2 dot squared and plus m small over 2 eta 3 dot squared. No cross terms, of course, right? Not of course, but no cross terms. Cross terms are possible, but not for a system like this, right? Again, 1 over 2 stays outside. We're not taking it into the kinetic energy matrix. So now we can write kinetic energy matrix because, okay, let me write again. In general, so it's a 1 over 2 Tij eta I dot eta j dot. Again, you see 1 over 2 is not part of the kinetic energy matrix. So T equals m small 0, 0, 0, m capital 0, 0, 0, m small. So this is our kinetic energy matrix. And you know what? I feel like since at some point soon I will start erasing, I will have to start erasing, and this kinetic energy matrix will be erased also. Let me rewrite it over here. I feel like there is a space. Let me move it over there. All right. T equals m 0, 0, 0, m capital 0, 0, 0, m. Okay. So now I feel better. So this and that. So that's it. So beginning of the problem, and now we just need to start moving through the typical procedure. Of course, as usual, we start searching for a solution, right? In this form, eta with I, ci a what I and e to the power of minus I omega t, which leads us to the set of algebraic equations, right? Okay, which we call eigenvectors, eigenvector equation, right? So let me write that down immediately. So eigenvector equation I can write immediately. So it will be v minus omega squared t, then column of our amplitudes, right? Basically eigenvector, and equals to 0. And of course, yeah, this is the system of linear algebraic homogeneous equations, and a non-trivial solution only possible only when determinant equals to 0, right? So we're getting characteristic equation, right, or equation for eigenvalues, right? Right. So for a non-trivial solution, so we have to demand that v minus omega squared t determinant equals to 0, right? As a result, immediately our system becomes underdetermined, giving us some freedom to normalize eventually our eigenvector. So it's over there. It happens over here, basically. Okay, so now, yeah, I can erase this. And so now we can write, yeah, I will write this determinant because, and I will keep it over there because I will need it. Okay, that form, I will need it several times. So it will be v minus omega squared t equals, okay. So it will be, v is here, so it will be k minus omega squared m, right? Then off diagonal elements 0, so pretty much they will be all here. Off diagonal elements will be constructed by the off diagonal elements of the V matrix. Okay, let me write first diagonal elements and then I'll fill out the rest. So it will be 2k, next one, 2k minus omega squared m capital, right? And then the last one will be the same like the first one, k minus omega squared m. Okay, and now of diagonal elements, I will just rewrite those. So it will be minus k, 0, minus k, minus k, minus k, and 0. Actually, I wrote down the matrices, but I didn't check. But I'm sure, yeah, they were correct. Just for any possible silly mistakes. No, it's good, 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 good. Of course, yeah. Right. Yeah, and of course it must be equal to 0. Okay, I'm not going to open this determinant. It's a tedious work. You know how to do it, right? Relative, I don't know, for example, for the first line, to the first line, or whatever method you want. You can use it, and of course you can solve it. You will get 3 eigenvalues, 3 normal mode frequencies. The first one is 0. Then the second one will be, surprise, surprise, k over m, like a frequency over isolated simple harmonic oscillator. There will be probably some finicky stuff so that frequency will be equal to the frequency of the simple harmonic oscillator, single simple harmonic oscillator. And omega 3, more complicated, omega 3 equals to k square root of k over m and 1 plus 2m small divided by m capital. Right, so 3 eigenvalues or frequencies of normal modes. Normal mode frequencies. So eigen frequencies or normal mode frequencies. Okay, so after this, of course, we need to, for each particular eigenvalue, we need to apply it back to this, because what does it mean? What we found, only with these frequencies, 3 frequencies, this function can be a solution of our second order differential equation, right? Only with these frequencies. So now we need to grab each of those, plug it, and see actually amplitudes of those solutions, which are eigenvectors, right? So let's start with the first one, of course. I will put first blue bullet, right? And omega 1 equals 0. Omega 1 equals 0, right? So, okay, and of course, let me show that. And now we need to plug it in our eigenvector equation. So it will be v minus omega 1 squared t a1 equals to 0, right? Eigenvector equation. And of course, what we have in the bracket, in a parenthesis, it's over what we have over here in this determinant, of course, basically, the structure. So that's why I wanted to have it somewhere at the top, because I will have 3 modes, and we will have to recycle the structure 3 times, right? Okay, so now just by looking at this and applying omega 1 equals 0, I can write what we have here in the brackets. It will be equal to, okay, k minus, omega equals 0, so it's simple. I don't have to think. K minus k 0 minus k 2k minus k, and then 0 minus k k, right? And then, of course, column of amplitudes of particles in the first normal mode, right? Which is basically eigen vectors. So it's you remember 1 1. The second index tells us about the mode. So this is the mode number 1. First index tells us that this is particle number 1, right? Actually, amplitude of the particle number 1 in the first normal mode. So now second particle, amplitude of the particle 2 in the first normal mode. And then, of course, amplitude of particle number 3 in the first normal mode, and it must be equal to 0. Again, what does it mean that we demanded determinant equals 0? It means that, oh yeah, determinant equals 0, so it means that in this matrix, one row or one column can be written as a linear superposition of the rest of the rows or the rest of the columns, right? In this case, for example, the last row can be constructed out of the first two. You can, for example, add them up and multiply by -1, you will get the last column. So it means that out of three algebraic equations, one is linearly dependent. Linearly dependent, it means it's useless. It doesn't give us any additional information. So we basically have a system of two equations with three unknowns. Underdetermined system. It's a consequence of this fact, of course, right? Okay, let me emphasize that on that. So it's a underdetermined system. System of algebraic equations. So effectively, two equations and three that doesn't look like n, and three unknowns. Okay, so it means that I'm not going to write three equations. I will probably pick the easiest one, the easiest ones, and obviously I think I will use this one and that one. The last one with three terms, I forget about that, right? Anyway, it's a linear combination of the other two, right? Okay, so now I can write it explicitly. So it will be k a11 minus k a21 equals to 0. So just the first row with that column, and now the last one. So it will be minus k a21 plus k a31 equals to 0. So this is our system again, as I told you. Three unknowns, two equations, underdetermined, right? So from the first equation, of course, we're getting that what a21 equals to a11, and from the last equation, from the second, a31 equals to a31 equals to a21. So now we can you can either call a11 as alpha, or usually I call it 1. Okay, so if I'll write if a11 is 1, all right, then of course a21 equals to a31 equals to also 1. Okay, now let me introduce normalization factor, because you remember I told you, right, since we have underdetermined system, we have some degrees of freedom, which which over here we're now trying to apply. I'm going to introduce normalization factor, and we're going to find that normalization factor so that our eigenvector will be normalized. All right. According to the procedure which we introduce as a normalization procedure. Right. Okay, so now as a result, we can write so the first eigenvector alpha 1 1 1. Alpha is a normalization factor. Let me write it down. Alpha normalization factor. Right. Okay, so now let's find alpha. And we have normalization procedure. So which is A1 transposed T A1 equals to 1. That 1 on the right hand side is just a number 1, right? Okay, so now let's write that explicitly. So column, okay, so alpha from there, give us alpha squared, alpha 2, alpha squared, then 1, 1, 1. Then kinetic energy matrix M 0, 0, 0, M capital 0, 0, 0, M small, and then column 1, 1, 1. And it must be equal to 1. Okay, we can easily multiply that. So it will be what? Let me write one more line. 1, 1, 1. And here we're going to get a column of M small, M capital, M small. M small, M capital, M small. Right. And now if we multiply them, you will get again alpha squared and 2m small plus m capital. 2m small plus m capital, and it must be equal to 1. So as a result, we're getting a normalization factor, right? So alpha will be equal 1 over square root of 2m small plus m capital, and we can close square root sign. Okay, so now we have the first eigenvector normalized. Yeah, and I forgot to mention about the great news. Come on, when we wrote down these eigenvalues, our frequencies of normal modes, there is no degeneracy. It's a great news, right? So you don't have to drag some of these eigenvectors through the Gram-Schmidt procedure in an attempt to normalize, in an attempt to make them orthogonal to each other, right? So in this case, no degeneracy, so automatically all eigenvectors which we are going to get are going to be automatically orthogonal to each other, which is great. So we just need to only normalize them, right? We proved it. Okay, let me emphasize, no degeneracy. No degeneracy. And of course, big happy face. Right. I forgot to emphasize on that. Okay, so now let me write finally form of first eigenvector. You know what? Probably I will write it here. I think I will be able to squeeze it. Right, to save space, 1 over square root of 2m plus m capital and column of 1, too big, 1, 1, 1. Okay, so let me frame it. Actually, no, I will have to erase it, so probably. Okay, I have in my notes, you have in your notes. Okay, so now let's just, okay, what we got. Again, what is the meaning of eigenvector? It's a amplitude of the first particle in the first normal mode, amplitude of the second particle in the second normal mode, in the second particle in the first normal mode, then amplitude of the third particle in the first normal mode. Right, so now we can draw a simple diagram describing the first normal mode. Right. So now I can draw something like this. So we have small mass, bigger mass, and again small mass. M capital, M small, M small. And so what happens? They all get displaced in the same direction by the same absolute value. You see, all positive. So it means that we have what? Eta 1, eta 2, eta 3. All right. And since they get displaced by the same value, so the separation between atoms are going to be the same. Basically, the whole system, the whole triatomic molecule just basically displaced in this direction. But of course, you need to remember that all these etas are small because we use Taylor expansions from the very beginning. So we're talking about small still displacement. But the whole system gets displaced in a certain direction. What is strange about this? Might be strange. Okay, but let me write first. So let me describe quickly this mode. Displacements. Okay, the displacement is the same for all. Okay, for each atom. The displacement is the same for each atom. For each atom. What is still strange might be strange, right? And it means that the center of mass moves. The same and and the center of mass moves. Right. What is strange is this. Our system, is it isolated? Yes, it is isolated system. So it means that there are no any driving forces, external forces acting on the system during the motion, right? And how come that center of mass gets displaced? And the thing is, yeah, it's still isolated system. It is an isolated system. But in order to create this mode, of course, you need to apply a particular initial conditions. Initial conditions must be applied, right? All right. You need to disturb your system with your initial conditions. Otherwise, you're not going to have any oscillations, right? So you apply initial, and for this, in order to trigger this mode, you need to apply initial conditions so that, and again, you remember what's the difference between initial conditions and the driving force? Because in both cases, you sort of apply external influence on the system. And the difference is this. Initial conditions, when you apply forces, right, in order to create initial conditions or pushing something, right, you do it all before t equals 0, because you start describing your system at the moment of time t equals 0 when you stop acting on the system. But driving force acts on your system throughout the whole motion. Right. Here we don't have any driving system during the motion, right? So it's isolated. But we do apply some forces in order to apply initial conditions, right, at the very beginning, before you start describing the system. So in order to trigger this mode, you need to apply some forces before t equals 0 in order to trigger this mode. And those forces you apply it in such a way so that, yeah, center of mass gets displaced, right? But still, system is isolated. So we're not violating anything. Right? So you need to see the difference between forces acting throughout the whole motion of this on the system, driving force, when the system is not isolated, and the system which is isolated, but you still need to apply some initial conditions. But of course, you apply those influences, forces, before you start describing the system. Right. So in this case, center of mass still gets displaced. Right. Okay. So now what? Let's look at the second mode. Second mode is with the frequency of an isolated particle, right? One of these, right? One of those. So now, yeah, it's time to, you know what, I will be able to squeeze a little bit into this part of the whiteboard. So now I can put the second bullet. And so omega 2. Okay, now I will skip lots of steps. Right, I will just get through key points, right? In the first example, yeah, I went through writing all the columns and matrices, but now I will write less, right? So omega 2 equals to square root of k over m, because I'm sure that you solve problems like this in math methods, right? So you're familiar with the structure. of the solution, structure of the solution, right? So now, of course, eigenvector equation, right? So it will be v minus omega 2 squared t, and eigenvector number 2 equals to 0, right? Of course, so now what? Again, I will use this structure of this determinant, right, in order to write this matrix, right? Right. Okay, so omega 2, it's this squared times this matrix. Oh, this, okay, we already subtracted, right? So, sorry. K over m instead of omega squared, so m gets cancelled, k minus k, 0. 0. Then, okay, so let me write again diagonal elements, and then the rest will be as in this determinant. K over m, okay, nothing gets cancelled. So it will be just 2k minus, yeah, 2k minus k and ratio of m capital over m small. Okay, let me check. Yeah. And the last one, the same like the first one, 0. Okay, and now I'll just need to rewrite those minus k, 0 minus k, and 0 minus k. And now column of amplitudes of each particle in the second normal mode. So it will be A12, A22, A32. Again, the last index tells us that we are in the second normal mode. And it must be equal to 0. And again, the system is underdetermined. So we have to write only 2 equations out of these 3. And the thing is, the first and the last one exactly the same. So we have to use either of those, right? So I will use equation number 1 and equation number 2. So here I don't have option, right? So I will use these 2 equations. Equations constructed by those 2 rows of the matrix. Okay, so you can easily write it down. I will just write that out of here. You will get that A22 will be equal to 0. Right. Actually, it's from the first equation immediately. You can see it. K times this element must be equal to 0. Right. And A32 equals to minus A12, right? Again, that can be obtained from the second equation, right? Okay, so the same, if A12 equals to 1, right, you can write down the second eigenvector. Oh, it's a second eigenvector, not the first one. A2 equals, again, I will introduce normalization factor alpha, right? And A12, I assumed 1. Then A22 will be 0. It doesn't matter what I assume. It means that the second particle is at rest. And A32 minus 1. And then, of course, if you again apply a normalization procedure, right, which is like this, but with A2. So then, if you apply a normalization procedure, which is A2 transposed T A sub 2 equals to 1. Okay, it's difficult to write. Okay, let me just write that down, the final form of the eigenvector, and we'll call it a day, right? And so now, if you apply that in a very, very similar way, it's just tedious writing, lots of writing, so you will end up with A2 equals, okay, so where is my normalization factor is 1 over square root of 2. Okay, 2m, right? And 1, 0, minus 1. So that's the eigenvector describing the second normal mode. So what happens in this mode? Okay, at next class I will probably draw the picture, right? Like as I told you, there was at STL, there is a researcher physicist, right? He likes showing funky moves, describing these modes of CO2 molecule, right? So he usually uses his head like the middle big particle and fist like small particle. So in this case, the middle particle stays at rest, right? And these particles, outer particles, they oscillates out of phase, right? So basically this stays at rest and these particles like this one, right? The center of mass stays the same in this case. And the last mode, which we will quickly write down next class, again, I'm not going to write much. I will just write basically the answers. The mode will behave like this. Again, trying to keep the center of mass at rest, right? So the head moves out of phase with these two particles, right? But these two particles are going to move in phase, but with amplitude, larger amplitude relative to the amplitude of the center of mass, sort of like this, right? So these two masses move, let's say, that direction, and the head will move slightly in the opposite direction. No, this way, right? Again, in order to keep the center of mass at rest, right? Like in this case, but not in the first case. Okay, so that we'll quickly discuss next class, then write model matrix and made a transition to normal coordinates. And then I will talk about tricks which can be used sometimes in order to deduce the transition from these coordinates eta to normal coordinates. But again, the system must be reasonably nice, right, in order to see it from the very beginning. Otherwise, safe approach is this approach, right? Very tedious, very sometimes even boring, right? But within an hour or two, you can solve the problem.